So to understand why resistors get warm, we just need to think about the fact that energy is always conserved. And so if a power supply or battery is pushing electrons, using energy to push electrons through a circuit, that energy has to go somewhere. And in our lab, we saw that resistors got warm. That was evidence of that energy. In this section, we're going to talk about power, the rate at which energy is being given to or taken away within a circuit. So remember that this is the formula for power from earlier in the year, sometimes written as power equals work over time. In this case, I've written it as delta E, or the change in energy over time. Keeping in mind the units, this will help us in the next step. This means that a watt is defined as a joule divided by seconds. So if we take that description, that watt is a joule per second, I'm going to play around a little bit with the units so that they're talking more about the types of quantities we use in electricity. In circuits, we focus on joules per coulomb, that's what a volt is, and then coulombs per second, that's an amp. And so it turns out that a watt is a volt times an amp. That's another way of sort of defining what a watt is. And that leads us to our formula for power that's more specific to electric circuits. P equals V times I, or power equals the voltage times the current. So take a look at this circuit here. If we wanted to calculate the power provided by the battery, we would need to know what the current is in this circuit. So that'll be our first step. Find the current that flows through the circuit. In this case, we'll use the previous idea, Ohm's law, that V equals I times R, and putting in the information we know, that the voltage provided by the battery is 6 and the resistance of the resistor is 600, we can divide and see that the current is 0.01 amps. And now we can calculate how much power, the rate at which energy is being provided by the battery. We'll use this new formula, P equals V times I, and our voltage of 6, our current of 0.01 amps. Putting that together, we see that the rate at which energy is being provided is 0.06 watts. Now, that energy is being also taken away or dissipated by the resistor. So the energy in is equal to the energy out. Let's take a closer look at that. So if we wanted to calculate the power dissipated by the resistor, again, we could calculate it in the same way, but if we wanted to really focus on the value of the resistance, this is something we'll need later in our course, we might rearrange our equation a little bit to allow for this. And please note that the voltage we will assume to be the same across the resistor as across the battery. We saw in the lab that there is a slight difference when you measure with a voltmeter across the resistor or a light bulb. It's just slightly less than what the power supply or battery provides. But if we assume our wires are ideal, that they have such a small resistance compared to the rest of the circuit that they can be ignored, then the voltage across this one resistor would be the same as the voltage through the battery. So let's take a look at this equation, P equals V times I. Knowing that voltage is current times resistance, V equals I times R, we can substitute an expression for that letter V. So changing it from V times I to IR times I, and then using some algebra saying that this would be I squared times R. Again, this is something that's going to be coming up later in our class when we look at more complex circuits. But if we plug in our information from before, a current of 0.01 amps, resistance of 600, we will get that same 0.06 watts. The energy provided by the battery is the same as the energy dissipated by the resistor. Another way that we might look at this, and again, we'll see this in later parts of our class, is instead of substituting in I times R for the V part of the equation, we're going to get rid of the I. Okay, we're going to think that from Ohm's law, I is V divided by R. And so we'll put that into our equation instead and eliminate the current, eliminate the I part of the equation. And so we get that power is voltage squared divided by the resistance. And again, this is just another way of calculating the same value. We would again get 0.06 watts. This will make more sense as we continue on to more complex circuits. But the main idea that I'd like you to understand from this is that the energy dissipated, okay, meaning the rate at which the energy is dissipated, the power, must equal the energy provided. So 0.06 watts used, given off as heat by the resistor, that equals 0.06 watts provided by the power supply or the battery. Let's take a look at the other way of thinking about power, power being the change in energy over time. So in this question here, we are told what the power rating is of a certain device, a laptop computer. So this tells us the combination of voltage and current that is running through the entire computer based on what voltage is used and what current is moving through it. We can take our kind of old equation for work and power, okay, P equals W over T, or P equals delta E over T, and we can use this along with the time that we're using the laptop for to figure out how much energy is going to be consumed. One thing to notice is that we're given the time in minutes, and that's not our standard unit, so we would need to convert that. Okay, how did I do that? Well, there are 60 seconds in a minute, and so if I multiply each minute by that 60, 45 times 60, I would get a total of 2,700 seconds. All right, so again, power is delta E over T. Let's rearrange that so that the thing we're looking for, the energy, is by itself. Multiply both sides by T. And that way we can put in our power and our time. And if we think about that 70 watts as really what it's defined to be, 70 joules per second, the units make a lot of sense that this comes out in joules. Now, if we have a more powerful item, like a gaming computer, that has a power rating of 500 watts. It uses much more energy than something like a laptop computer. And let's also assume that we're going to play with this a little bit longer, so 4 hours. So again, we would need that 4 hours to be changed into seconds. 60 seconds in a minute, 60 minutes in an hour. So 4 times 60 times 60 is where this 14,400 comes from. But going through the same process of multiplying the power times the time, we see a much larger amount of energy use for our gaming computer. All right, well, that means it would cost more too, right? I mean, energy isn't free. How does that work into all of this? Well, if you were to look at a power bill, okay, this is a power bill from Ameren, which is our local power company. It's a little hard to see, I know, on the screen, but the rate at which you are using energy, consuming energy, is not actually measured in joules by the power company. The power company uses a unit called a kilowatt hour, which doesn't quite look like an energy value, but it actually is. Okay, recall from the previous problem that energy was power times time. And so if the unit is a unit of power, kilowatts, times time, hours, this would be an amount of energy. It'd be kind of like, instead of calling it a joule, if we called what we were talking about before a watt second. Well, this kilowatt hours is actually what the, again, what the power company uses to measure energy. It's a much smaller value, not those crazy, millions of joules that we were just talking about. And so it's a little bit simpler for them to deal with. In Champaign, we pay about 13 cents per kilowatt hour, or $0.13 per kilowatt hour. And that takes into account everything, the taxes and the handling fees and all sorts of things that you're charged by an electric company. So let's see how much that laptop use and gaming computer use would cost us. So instead of leaving our power in watts, we're going to have to change that to kilowatts. And instead of changing our minutes to seconds, we're actually going to change the minutes to hours. So using the same formula, power times time, we're just going to use different units to represent the power and represent the time. So converting 70 watts to kilowatts, converting 45 minutes to hours, we get that the amount of energy measured in these other units is 0.0525. And then since each kilowatt hour costs us 13 cents, we can multiply and find out what the cost of using our laptop computer is. So not too much, not even a penny, not too bad. Now, our gaming computer has a much higher energy use, and we're using it for a longer amount of time. So I would need to, again, change that 500 watts to kilowatts. The time is already in hours, all right? So we would be taking 0.5 kilowatts times 4 hours. And this tells us our energy usage is, again, much greater, a full 2 kilowatt hours. And that means that since we're charged 13 cents or $0.13 for every kilowatt hour, that would be 0.26 kilowatt hours. Now, it doesn't sound like too much, about a quarter to play for that time. But if you were to do this every day for a whole year, that actually ends up adding up to $95 just for the electricity of your computer. So something to keep in mind when you're using electricity in your home.